Okay, so in the first lecture here in week 4, we're going to take a look at something called data cleaning. Often when you get some data from some place, from a comma separated value file or downloaded from a website or what have you, it will have a variety of problems, and we need to know how to address those. I'm going to skip these 2 review questions. You can take a look at those on your own about data frames. Okay, so data cleaning has to do with making sure that the data is good for the purpose of doing statistical analysis on it, displaying reports that make sense, etc. Very common kinds of problems in data include data that's missing. If you have a collection of patient records for a clinic, you might discover that for 12 of your patients you don't have an age, and for 5 of your patients you don't have a phone number or something like that. You can also have duplicate data. You might, in the same kind of example, have some patient who's for some reason in your database 2 times. You might have data that's out of range. You might have data that's in a bogus format. You might have round-off errors. All kinds of these kinds of problems, and we're going to take a look at how to solve or how to address solving several of them in this lecture. If you're lucky, you'll have some formal requirements for your application that will tell you how to clean up the data. For example, if you're processing information about employee salaries in a company, there might be an actual written requirement for you that if you pull in information about an employee and discover that the data for the salary for that employee is missing, then you're instructed to replace that with the mean salary. It's uncommon to have these kinds of very specific requirements. Very often the data analyst is sort of left up to his or her own devices to figure out what makes sense. Okay? Now, if you are producing information for someone else in your same organization to read, or some other program in your same organization to read, or vice versa, that is, if you're reading data from a file that was produced within your organization so that you have the ability to communicate and control what is in those files, that's great. But very often you'll find yourself getting data from some outside source, and you may not have any control over what's put into that file. So you'll end up with missing data or inconsistent data or improperly formatted data or what have you. Comma-separated value files are a very common way of sharing information, but what do you do if you read a comma-separated value file into your application and you discover that something is, that you just have a couple of commas together indicating that that something is missing? Well, without belaboring this and reading the slide to you, you just have to decide what to do. Do you replace the value? Do you eliminate the row? Do you replace the value with some kind of average? What do you do? Here is a function that we have written called goodData that looks at a line of input and tests various things about that line of input to see whether the data is in a format that we can accept. All right? We are expecting lines that we read from our input to have 4 fields, and line here is coming in as a list or a tuple, let's say. So the first thing we're going to do is to check whether the length of the line is exactly 4. If it's not exactly 4, we're just going to return false. That's a bad line of data, and we may decide to just skip that line altogether. Having concluded that there are 4 fields in the in the line, however, we should then go through and check each item in the line, and in this case, we're going to see whether the item itself is empty. All right, if the items in this, if the items in each line are strings, for example, we can compute the length of the string, and if the length of the string is 0, then we'll again return false because it's an improper line of data. Only if both of these tests for the length and for the lengths of each items succeed do we return true. Here we have some mainline code that's making use of this good data function. I guess I won't try to highlight it here. Let me show you this in a code file. All right, so here's our good data function up above that evaluates whether the line that's been passed in has 4 items in it, and also checks each item to see whether the item itself has any text in it. And here down at the bottom is our mainline code. We're going to create for ourselves a list called data. Here I've created the empty list by using the conversion function with empty parentheses. I could have also said data gets open and close square brackets equivalently. And I'm going to open this comma-separated value Csv Data.csv file for reading. I just want to show you what that file contains. All right, the contents are shown on the next slide. All right, so this is our Csv Data.csv file. And you can see that many of these lines of input here from the CSV file have things missing. Whoops, okay. So we're going to read each row, that is each line, from the input file, one line at a time. We're going to strip off the new line character at the right-hand end of each row and split each row at comma characters, okay? So each one of these rows, each one of these lines is going to be split into a list of fields. Then, if the list, my list, describes good data, that is, if there are 4 fields in the list and each one of those fields is non-empty, I will append the data for that particular line to my entire list of data. Whoops, I lost my. I better have data be an empty list up there. And when I'm all done, I'll print out my data. Now, if we take a look again at the data file, you'll see that the first line has 4 non-empty fields. The last line has 4 non-empty fields. But the second line has a missing field. The third line has 2 missing fields. The fourth line doesn't even have the right number of fields. It's only got 2 fields instead of 4. So when I run my code here, all that ends up in my valid data list is the list containing the fields from the first line and a list containing the fields from the last line. Okay. Okay, so that's an example of just throwing away any data that isn't perfect. And the bad news, as you saw, was we started with 5 lines of input, but we ended up with only 2 lines of good data. Maybe we could have been more clever to try to rescue some of those imperfect data lines to make them usable. Okay. I don't think there's really anything terribly... yeah. So in our code here, we're saying if the data is good, add that data to the list. We might also want to add an else in here following the if so that we can try to patch up the data. All right, so if a particular line of data is, or a particular list of data is not good, maybe we can evaluate what the missing fields were and fill them in with something that makes sense. Or in the case of our one data line here, JK, that only had 2 fields in it, maybe we'll decide, well, that one is so damaged, we're not going to try to figure out how to solve that problem. Okay, so we can throw in some more logic here in an if to try to do a better job of cleaning. Here's another way of handling that file. This time we're reading it into a data frame using the Pandas read CSV file. That will get us every one of the lines of input, and anything that's missing or improper will just get filled in with a nan. Now, in order to do that, I had better remember to import Pandas as PD first. And later on, I'm also going to use some NumPy stuff. So let me also import NumPy as NP. All right, so here once again is my file. Okay, and if I say data gets pd.read CSV of CSV data.csv. Now, the data file, if we looked at it, does not have any column names in it. Let me pull this back again. This data file does not have any column names in it. Likewise, it does not have any row labels in it. It turns out that when we call read CSV, we will get row labels of just sequential integer values, 0, 1, 2, 3, 4. For the column labels, well, this is inconsistent. I don't say columns and then specify names for the columns. So what I do instead for read CSV, and we can, yell at the designer, is we say names gets whatever we want the column names to be. I'm just going to call them 1, 2, 3, and 4. All right, so there we are. So now data has 4 columns named 1, 2, 3, 4, 5 rows labeled 0, 1, 2, 3, 4, and for all the missing values, we get these not a number indications filled in. Notice for the 4th line, the line sub 3 here, read CSV just makes this assumption that, well, okay, if there's supposed to be 4 columns, but I was only given 2 values, I'm just going to assume that those are the first 2 columns. And that may or may not be a good guess. We've used previously the is null and not null functions to test whether each individual item is null or not. So if I say data.isNull, I'm going to get a data frame, a Boolean data frame, in which I will have false for each item that is not not a number. Okay, so I'll have false for each valid item, and I'll have true for each null or not a number item. All right, so there's my two-dimensional Boolean data frame. I can use this Boolean index as a subscript into the data frame itself. So here's data. And if I say data sub data dot not null, okay, now not null is the opposite of is null. Not null is going to give me trues for all of the valid entries and falses for all of the invalid entries. So this is going to be kind of silly here because data sub this Boolean data frame is going to give me back exactly what I started with. So that's not a very productive thing to do, really. A better thing to do if I want to get rid of all of the rows where something is not a number is to use the drop na, NA for not available. I had to think for a minute. Sometimes NA means not applicable. In this case, it means not available. So if I say data drop na, then I will get only the rows where I have only valid data. And I can use the in place equals true parameter here to directly modify that data frame. Let me make a copy. Data copy is data.copy so that when I mess up my data by saying data.dropna in place equals true, I can see that data is directly modified. Data copy, however, is still left behind so that I can use it if I need it. An argument for dropna, the how argument, can be used to restrict how much stuff is dropped. The default for dropna is if anything in the row is not a number, then we'll drop the whole row. But if I say how equals all, that means we're only going to drop rows where everything is not a number. So let me restore data equal to data copy.copy. All right, so I'm making I'm recopying from data copy back into data. All right, and now I can say data.dropna how equals all. Notice that the default here, I'm not sure you can see that actually, but the default for how is any. So the default for how is any. Let me just show that. This is the default for how. And if anything in the row is not a number, it's dropped. But if I say data.dropna how equals all, then the row is only dropped if everything is not a number, and we don't have any rows in here where all of the items are not a number. Another thing you can do to deal with these not a numbers is replace. I can say data.replace not a number. Now, not a number, even though we're seeing that appear in a data frame, remember that each column in the data frame here is actually an ND array series, and the special value that represents not a number within the NumPy module itself is nan, and just to drive you crazy, it's nan in all lowercase. So I can say data.replace not a number with, let me just do something that's going to be really easy to see. I'll just use capital Z. So I'm going to, in my data, I'm going to replace not a number, whoops, that's supposed to be a comma, with capital Z. There we go. So where I had not a number, now I have capital Z. Okay. But that did not directly change data. I believe that replace has an in-place parameter. Oh. Okay, that's interesting. I'm not getting any data.replace. And yes, it does have an in-place. I don't know if you can, that may be a little bit below the recording, but it does have an in-place, so I can do that in place as well as getting back a modified copy. All right, so drop na, replace are some mechanisms for trying to patch up missing stuff. Here we're going to look at some, even additional things to try. We can use fill na, which is basically sort of like a shorthand for replace in a way. If I say data.fill na, that means to fill anything that's missing with, in this example, we're using an X instead of a capital A. And so you can see that we have X's in here. That does not directly modify the data. So actually the example here is not quite right, because doing the fill na produces a modified copy but does not directly change the data. Let's try a different file that has different data types for the different columns. This is my bonus.csv file, and it has 3 columns: name, years, and bonus. Name is obviously somebody's name. Years, let's say, is years of employment. And bonus is the most recent annual bonus that the person received. I'm going to read that in. I'm going to create a variable bonus containing the data frame read in from that file. In this case, the first row is used to provide the column names by default. The labels by default are going to be 0, 1, 2, 3. So when I take a look at this bonus data frame, that's what I see. All right, name, years, bonus are the column names, and the labels, the row labels, are 0, 1, 2, 3. I do have a missing bonus for Jones, and I do have a missing number of years of employment for Barnes. Now, fill na that we talked about before, by default is going to replace all occurrences of not a number with some value. So in slide 15 here, all of the missing values in data ended up being replaced with capital X. But it's not going to make sense for me to replace both the annual bonus and the number of years of employment with, the same value. So we can use dictionary notation as an argument to fill na to specify in which column we want to do this filling of not available values. Bonus.fill na of years 0. All right, so that is going to discover that Barnes has not available data, not a number data for years, and that will be replaced with 0, but the bonus is not going to be changed. And again, here the slide in the notes is implying that that directly changes bonus, but it doesn't. Bonus is unchanged. We could use the in-place parameter to make that happen in place. My dictionary can, of course, have multiple columns in it, so instead of only replacing years of employment with 0, I could also replace bonus with, let's say, 1,000. Oh, let's say 2,000. Okay, and so now I'm going to have years replaced with 0 and bonus replaced with 2,000 for Jones. Right? Okay, another thing we can do with fill na, in addition to specifying specific columns whose values we want to change, is we can specify a method. ffill means forward fill, and the upshot of that is that as we go through these records one by one, and these rows one by one, okay, when we're looking at row 0, we see years of 10 and bonus of 5,000. If we have said method equals forward fill, then when we get to line sub 1, Jones is there, 2.0 is there, but bonus is not there, and Jones's bonus is going to be filled in with 5,000. Similarly, when we get down to the sub 2 row here, Barnes is there, the bonus 1,000 is there, but the missing value is going to be filled in with 2. Okay, so this is something you can do. It's very unclear to me that this is really so useful, but let's just show that it works. So here is bonus, and if I say bonus dot fill na method is forward fill. Okay, I'm not going to do the in place. Well, actually, I guess, well, I'll do it without first, and then I'll do it with. So we got 5,000 filled in as Jones's bonus. We got 2 years filled in as Barnes's years of employment. And if I want that to be permanent, I can use my in place of true. All right, so that's a look at some methods for discovering and dealing with missing data. And I just want to point out, in case you haven't noticed this yourself, that all of these methods are very hacky and clumsy. And they're not really, it's not really possible to automate these in general terms. If you have a particular data set that you download on a regular basis, and you know in advance the kinds of missing data that you're going to see in that data set, and you can make decisions in advance about how you would like to handle the missing data in that particular data set, then these methods that we've talked about in the last several slides are fine. They can be programmed and they can be used. But you can't just download any old data set and decide, oh, well, okay, just as a rule, I'm going to use fill na with method equals ffill to solve my missing data problem. You know, for some data sets that might make sense. For other data sets, it's going to make no sense whatsoever. So the bad news, here we are at about the midpoint of this data cleaning stuff. The bad news I want to tell you is that this is very clumsy, very awkward, very data set specific, and often takes a lot of time and pain to clean up a data set to a reasonable degree. Okay, so in addition to dealing with missing data in some fashion or other, we also need to check the validity of the non-missing data. And this includes things like checking whether the data that we read in is within an acceptable range of values. If we're dealing with checking grades for exams, negative grades, grades greater than 100%, those are obviously not valid. We're also possibly going to need to check type constraints. So if one of the pieces of information that we read is an age, then if that thing is a string or a Boolean value, that's not going to work too well. If we are reading in data that's supposed to represent keys in a dictionary, let's say, then we have to make sure that the values are unique. We don't want data to be repeated in that case. And sometimes we have data, what am I trying to say here? Discrete data where the value must be one of the members in a particular set. So, for example, eye color here, we're not going to allow, well, I don't know. I was going to say we're not going to allow magenta eyes. Maybe somebody has magenta eyes. But, that would be another example where we need to check whether the value that's read in is a member of a recognized set of possible values. Okay, let's suppose here, given our bonus data frame, that we want to find out who has a bonus value that is greater than $2,000. This gets us back a Boolean series with true for each of the records in here where the bonus is greater than 2,000 and false otherwise. Maybe we're going to come down hard on bonuses. Our company is suffering some financial problems, and so we would like to trim back on anybody who has a bonus that's greater than $2,000. Well, if we try something like this, bonus sub bonus, where bonus sub bonus is greater than $2,000, all right, that gets us back bonuses that are greater than $2,000. And if we try to set that to $2,000, presumably these are planned bonuses, not previously paid bonuses. Well, we get yelled at that we're trying to modify a copy of a slice from our data frame because the selection here is not directly accessing the original data frame. It is instead extracting out a slice separate from the data frame, and we're attempting to modify items in that slice. So we have to use, so logically what we've done here is kind of the correct idea. It's just that in implementation terms, it doesn't work. So let's try something else. Let's get ourselves the Boolean series of bonuses that are too large. Okay. Hello? Oh, interesting. Interesting. So, okay, a value is trying to be set on a copy of a slice from a data frame. So I did get yelled at, as expected, and yet, for some reason, it does appear to have worked. All right, well, that's strange. Maybe it's a consequence of an updated version of the Pandas library that allows that to work. I'm gonna reset things so that I can demonstrate what's going on here on slide 20. So let me say bonus dot loc sub 0 comma bonus gets 5,000, and the same thing for 1 and 3. Okay. All right, so now we have Smith and Jones with bonuses of 5,000, Chen with a bonus of 4,000, and this will enable us to demonstrate using the Boolean index to select a collection of rows in which we can modify the bonus. All right, so let me recompute temp here. Temp gets bonus sub bonus greater than 2,000. Temp is now true, true, false, true. And if I say bonus dot loc, using that Boolean series to select the particular rows, and then asking for the bonus column, this is giving me, I know you can't really tell the difference, this is giving me direct access in that data frame to those bonus values where the bonuses are too high. And if I then say that gets 2,000, well, that would have worked if I had spelled bonus correctly. Let's try that again. Gets 2,000. Okay, so now everybody has acceptable bonuses, planned bonuses for the coming year. Okay, in this next example, we're going to demonstrate how we can invoke a function on each one of these values. And in this case, we're using a lambda expression rather than a named function. If I say bonus sub bonus, this is going to give me the entire column. And if I say bonus sub bonus dot apply, this will enable me to apply any function that I want to the values coming from this bonus series. And in particular, here I'm going to say lambda for argument x, let's compute twice x. On the slide, just to preserve space, we named our lambda function, our lambda expression, and then applied that lambda function. But here I'm just going to do it all in one statement. So each value coming from the bonus series here is going to be doubled. We pass in the bonus to the lambda, and what we get back is twice that. And this we can use to modify the values in the bonus column, right? So let me create a column, or let me create a variable to refer to that series of the doubled bonuses. And we know that if the number of items in a series is equal to the number of rows in a data frame, that I can replace the entire row by just... I can replace the entire column by assigning that other series to that column. There we go. So in that case, I applied a lambda. In this example here, I'm going to create a named function that I can apply to each item. And in this case, I'm just doing a check to see whether the bonus value is too high or not. And I'm going to return a string to indicate whether the bonus is too high or not. And I've arbitrarily changed my mind here about what represents too high a bonus. I guess our conditions have improved. So now I'm going to say, now I'm going to complain that the bonus is too high if it's greater than 3,000. So let me define this function, too high of some argument. If that argument is greater than 3,000, we'll return that that bonus is too high. Else, we'll return that that bonus is okay. There's our function. And now bonus sub bonus is the series of bonus values, and I can apply to that this function that I just defined. Okay, and so each bonus value in the column of bonuses is going to get passed in to this too high function, and what I'll get back is a series of strings in this case. Okay, so too high for the 4,000s and okay for the 2,000. Rather than modifying an existing column, we know that we can add a new column to a data frame by just giving that data frame column a name. So I'm going to say here, bonus sub classify. Okay, so bonus sub classify, this new column is going to get the values of this series produced by applying the too high function. And now I've extended my data frame by that additional classification column. I can also do validity checking of data types by using try and except. I can attempt to do conversions, and if the conversion fails, I can capture that by using except, and I can decide what to do to patch it up. The other option I have is the same that I have for missing data. I can just choose to skip the data if it's badly if it's in the wrong type and I can't figure out how to patch it up. One way I can check the type of a column is to ask for its D types. So here's years. Notice that if I display the whole series, I get told the D type. But I can ask for the D types, and I get told all of the D types of the values in this series. Well, for a series, there's only one D type, so that looks a little odd, but the cool thing is that I can apply D types. I can ask for the D types attribute of all of the columns in the data frame. And this tells me that years and bonus are float 64s, name and classify are objects. They happen to be strings, but in an ND array, these are represented as objects rather than strings. One way of modifying a data type is to invoke the as type function on a particular column or set of columns whose data type you want to change. So for years of employment, these are represented in the data as floats, well, float 64s, but they are actually integer values. We don't keep track of fractional years of employment here. So I can say bonus the as type, and here I can use my dictionary description to say for the years column, Yates, years column, let's apply an integer conversion. Now, this may look a little odd. I'm not sure that we've seen this before, but anything in Python is an object. Even a data type is an object, and so you can use a data type as a value in a dictionary. Here the data type is int, and so I'm applying that int conversion to the years, and hence I get the years converted to int. Now that in turn will be converted to int32 or int64 because the data frame doesn't directly contain Python int values, but that's okay. I can convert the float to I can convert the float 64 to a Python int, and then the data frame itself will automatically convert that Python int into an int64. Let me save this back into our bonus data frame. So now bonus has that column as integers, and if I ask for bonus.dtypes, I see that years is now an int32 column rather than an int64 column. Oh, interesting. Okay, so I guess on Professor Barrett's machine, it is an int64. All right, now on this next slide, 28, we're showing an example of how you can actually test what the data type of a particular column is. And in this case, we're just printing out either yes or no. You could do something more interesting than that. To get, this is sort of like, what am I trying to say here? This is describe. Okay, this is sort of like describe that does descriptive statistics. In this case, we're asking for the info about the data frame, and we get back all this information about the data frame. That there are 4 entries, the labels are from 0 to 3, there are 4 columns, we have the column names, we have how many items in the column are not a number, and we have the data types of all the columns. Interestingly, it's also showing us how much memory is actually being used to contain this data frame. Okay, now when you're dealing with strings, well, when you're dealing with various different kinds of data, dates would be another example. It's difficult to do comparisons of strings or dates or things of that kind unless you can guarantee that all of the values are stored in some kind of canonical form. What do we mean by that? Well, consider a person's name. we'll take my name, John Ostlund. Okay, well, my name could be represented as John Ostlund with a capital J and a capital O, or it could be represented as John Ostlund in all caps, or it could be represented as John, Ostlund in lowercase. If I'm trying to test whether some record refers to John Ostlund or not, there's a question of, what am I comparing? In other words, suppose that my data frame has John Ostlund with capital J and capital O in it, but the data that I'm comparing that to, for whatever reason, is represented in all uppercase. If I compare whether John Ostlund with capital J and O is the same as John Ostlund in all caps, well, of course, that comparison is going to fail. That's going to be false, and yet I probably do want to recognize this record as describing this person, John Ostlund. So when you are faced with a situation like this, where you're comparing things like strings, which may be of mixed case, or you're comparing things like dates, which may be in various formats. For example, in the U.S., we do month, day, year. So 12/1/2021 in the U.S. is the same date as 1/12/2021 in the Europe Convention, and probably elsewhere as well. Those are not going to compare as equal when you do a direct comparison as strings, but they are in fact the same date in just two different cultural settings. Okay, so we need to convert both the value that we're searching and the value that we're searching for to be of the same canonical form so that we can do valid comparisons. All right. This is just another example. The actual data frame, in this case, has Bob Smith and Laverne McCoy with conventional mixed upper and lower case. But if I need to compare that to data set that represents names as all caps, I would need to convert that to all caps. And by the way, this apply map function is a way of doing that. Stir.upper is the upper method of the stir class, and I can, well, let me just do this to a single string. If I say ASDF dot apply map stir.upper, whoops, has no, okay, so that, I'm sorry, that's a data frame method, not a stir method. I can do this. I can say bonus subname to get that column, and then apply map stir.upper. Oh, a series has no... All right, I'm going to stop fooling around here. Okay. Now, a very smart thing to do to avoid losing your original data by converting it directly to a canonical form is you can create a new table separate from your original data, and then you can concatenate the two tables together so that, the two data frames together, so that the merged data frame contains both the original form of the data and the canonical form of the data. And that way you can do much more, you don't lose any of your original information, and you gain the advantage of being able to do canonical form testing. So let's walk through this example. I'm going to create, here's my names. Whoops. All right, I guess I need to, I was hoping to avoid doing this example, but we'll do it anyway. Okay, so here's names, and this is the original case, and I can do the apply map of stir upper. To get the canonical form of everything capitalized. Now I'm going to save that as a new data frame. So names.applyMap of stir upper gives me back a copy of a data frame, and I'm going to use the pd.dataframe construction function to take that modified stuff and put it into a data frame. Notice here that the column names in this data frame that has the canonicalized forms of the first and last names has the same column names as the original data. And if I'm going to be able to append together the original data followed by the canonicalized data, I can't do that if I have matching column names. So here I'm going to rename in place first and last to their uppercase equivalents, right? So first is going to become first in all caps, last is going to become last in all caps. I'm doing this in place, and so now I have both canonicalized data and canonicalized column names. Here's what names looks like, and here's what X looks like. I can concatenate these things together in column sequence by using pd.concat, pd.concat, and give an iterable on my data frames that I want to concatenate. Now, by default, this would concatenate the two in row-wise order, but I want them in column-wise order. So I'm going to say axis is 1. And there we are. So now I have the same number of rows that my original data frame had, but now I have concatenated the columns together, and I'm going to save that into this variable new names. So let me do that whole thing. There we go. All right, and so now I can interact with this data frame and have access both to the original data and to the canonicalized version. If I don't specify any axis when I do the concat, or if I specify axis equals 0, then concatenation occurs on a row-wise basis. So if you do have, for example, suppose you had a whole bunch of financial information for the year 2019 and for the year 2020, and you wanted to concatenate those two together into a single long 2-year data frame, you can use concat to do that. It's also possible to do database-style joins of data. Okay, now, so that takes care of canonicalizing things like strings and dates. You may also require certain values to be unique if you need to use those values as keys for some purpose. If you were using a database, then the database software itself will enforce that a key can't be duplicated. But in Pandas, it's up to you to check whether you're accidentally using a duplicate key or not. All right, I've got this file, sales.csv. Let me pull up a copy of that thing. Where is it? I'm going to pull that into Word Notepad so we can see it. Okay, so there is the data frame. And I have day, salesperson, and sales. If I use read CSV to pull that in, here we are. Now, if I want to use day as a key, I have a problem here because I have Monday occurring twice. And I can use the drop duplicates method on a particular column to eliminate the duplicates. If I say sales sub day, that gets me a series. And if I say sales sub day dot drop duplicates, notice that the first occurrence is preserved and the subsequent occurrences of Monday are eliminated. You can apply drop duplicate to entire rows of data in addition to individual columns from the data frame. Here I'm going to modify my sales data frame by intentionally appending an identical row to a row that I already have. So here is sales, and into that I'm going to assign, or I'm going to, I'm going to do a sales.append of a duplicate record. The day column is going to be Monday. The salesperson column is Jones. Sales is 43.0, and so on. That will return to me a modified copy of my data frame, but I do want to save that into sales. So let me do this append. And by ignore index, I'm ignoring the row label here. So now sales does have an entirely duplicate row, and as we can see, I can drop duplicates without specifying, without doing that on a specific column. So this is applying drop duplicates to the entire data frame. By default, I would just get back a modified copy without changing the data frame. And so I want to use the in place equals true argument to cause that to happen in place. So drop duplicates is a tool that that the data frame data type provides for us to handle accidental duplicate values. Finally, if we want to specify or determine whether a particular value is in a set of values, this is usually going to involve string data fields in Python. as an illustration, let's take a look at days of the week. We can test whether a particular string is in a set of recognized strings. So I'm going to create days as a set here, and I'm only allowing work days. So, whoops, too many. Let me try again. I hit paste twice. All right, so I'm creating a set here, Monday, Tuesday, Wednesday, Thursday, Friday. Perhaps I'm only going to allow my employees to work, to not allow weekend days to be used. And in my sales data frame, you'll notice I've got an accidental Fleurs Day down here. So I can ask for sales.day. Actually, I can say sales.day since day doesn't have a space in it. I can select the column that way. Sales.day, I can apply the test of whether the value of a particular row is in the days set. Okay? And this will give me back a Boolean index. Invalid syntax. Okay, it's entirely possible that I can't use apply following the dot this way. I don't believe... Right, so I'm going to just retype this thing using the subscript. There we go. Oh! No, silly me. Lambda. I forgot my B. Lambda. There we go. Yay! And now it works. And so I get told that that the day value in row 4 is not recognized. Okay, so to sum up, cleaning data is an awful experience. It really is. Very often, cleaning data just takes, 10 times as long as you think it should. You have to deal with missing values. You have to deal with incorrect values. You have to verify all of the data to make sure that they're in the correct range, or that they are in, that they're a member of the set of possible values. On and on. It's all very hackish, frustrating, slow. And basically, what we've done here is we've kind of done a brief survey of mechanisms that the data frame provides for helping you with this painful task. Okay, so that's that.